Hello, hello. We have a problem in rotation. I'll be starting a series of problems today on rotation, so do check later on for other problems and concept related to rotation. So here we have a an ultracentrifuge. Ultracentrifuge is basically a centrifuge that spins at a very high rate. What's a centrifuge? Well, it's a kind of device in which you have a container where you kind of put a material, it's a liquid material with some particles in there, and it kind of spins. It's attached to a motor which spins this whole thing. This whole thing spins around, and so that's something used in labs, biochemistry and biology labs. Okay, so we are told that it's supposed to spin all the way to 150,000 rpm, starting from rest. Starts from rest and takes about 5 minutes to reach maximum rate, and it's going at a constant uniform acceleration. So in a past video I defined all of this, so we can say that this axis is axis rotation and it's some fixed axis z using capital Z. This is and we mark a line or another axis that rotates with the rotation. So this was like a little x, and the little x at time 0, little x at time delta t. So this is the angle delta theta that rotates, and the description here is so angle of rotation delta theta is a vector with amount delta theta, and the direction, this is k hat direction, k hat. So this is a vector representation, and angular velocity is, because this is fixed or fixed direction. So another way to tell the direction was that this is going counterclockwise. So we look at this counterclockwise. But I find using the vector is much simpler rather than counterclockwise and clockwise. That's too much writing. And this is just a delta theta over delta t. So d theta over dt is still k hat, and alpha is the angular acceleration, which is also a vector, and it's a derivative of d omega dt. So this is also fixed. So when we write is omega k hat as a notation, and this becomes just d omega dt k hat also. So it says a constant angular rotation means this thing is constant. This is already constant. So we have a d omega dt is some constant alpha. Then you can see immediately that omega will be at some time t. At some time t will be omega at 0 plus alpha 0 amount of time elapsed. And because now we know omega at time t, and this is omega at time 0, so omega at time t, this equation can be, I put it d theta dt equals to omega. So it will be d theta dt will be omega at 0 plus alpha 0 t, and that will make theta at time delta theta, integrate this, will be omega at 0 t plus half alpha 0 t square. So these are this one equation, and this is the second equation, and you can kind of get rid of t from there, and you will get a omega at t square equals to omega at 0 square plus 2 alpha 0 delta theta. So this is from here, these two you can get number 3 equation. But these are the equations which you can use for constant angular acceleration. So now let's see what the problem is. Sometimes this already listed in your book. This is the first time I'm doing this, so I just want to derive this quickly. Okay. What is the average angular acceleration? So I'm supposed to find alpha. What's given is omega t at omega 0. So given for us is omega 0 is 0 and omega t is 150,000 RPM. So I'll just keep it in RPM first, and you can see that and also given is time taken is 5 minutes. So this minute and this minute is the same, so I just keep everything like this. No need to change units. And first thing to find for A is angular acceleration. So A is going to be angular acceleration. So alpha, which is alpha 0, is just constant angular acceleration, will simply be, we just use this equation, and this minus this divided by t. So it's going to be this divided by that. So that's going to be omega t minus omega 0 over t, and that's just 150,000 minus 0 over 5, and so this will be 30,000 rev per minute square. So we got into this, and we'll change the unit later. Okay, let's work out the B. B is how many revolutions did it take to get to the final angular speed. So I'm supposed to find out delta theta. So in here I know everything, so I can just use this. So delta theta is, I just found out 30,000. This is 0 plus half times 30,000, 5 minute square. So minute square will kill minute square, and it's going to give me revolutions. So we have 15,000 times 25 revolutions, and so you got thousands, and then 12 plus 25 will be 37, I think. Yeah, this many revolutions. Okay, so that's the answer. Okay, now converting units. So in one revolution, you go 2 pi radian, which is 360 degrees. Okay, that's and we need minute. 1 minute is 60 second. So it's rather easy to convert. So alpha 0 is going to be 30,000 rev per minute square. So rev I need to convert into radian over rev. So 1 rev is 2 pi radian, and I need to convert minute square. So there are 2 factors of minute. So 60 times 60 second square, minute times minute. So this 2 minutes, this is the main place you might make a mistake, because you need 2 factors of this. And so revolution cancels revolution. So you can just work out the numerically, this will be the answer in radian per second square. For delta theta is even simpler, you just multiply. For delta theta, you will have a 375,000 times 2 pi radian. R is going to have a 375,000 times 360 degrees. So you just multiply them out, and that's the way you can convert them. This is a very good introductory thing, and I would recommend that most of the problem that you encounter are going to come up with a constant angular solution. In that case, these 3 formulas, you can memorize them and use them again and again in different problems. And you don't have to derive it all every time you look at them. Okay. I'll see you in another video. Bye.